recording now. We should be live. All right. So folks, um, what's happening today is we're gonna do some calculations of some Riemann sums. I told you that Riemann sums, folks, and I'm going to write here. Riemann sums are nothing complicated, are just the areas under the graph of a function calculated with rectangles. So rectangular areas under the graph of a function, you can think of that. So rectangular areas under, oops, move that out of here, the graph of function. All right, so this is pretty much all you have to remember. Oh, I want to calculate the area under the graph of a function. Well, I'm working with these rectangular areas, which means that we build rectangles under the graph, something like this. We put them next to each other. Now this is not particularly a good definition, rigorous definition, but it gives you at least an idea of what's happening here when we calculate these areas from A to B. Let's say A and B are some numbers on the real number line on the x-axis. All right, so this is a Riemann sum. Now we're going to calculate such things. So again, abstractly, I wrote them abstractly last time. I'm not going to write them again as a sum of f of xi times delta xi. So when you have things like that, you would want to make sure that you understand the concrete situation that's given there, because in practice nobody does abstract sums and random subdivision points like they imply in the book. So of course, again, the theory of these integrals, I told you, it's a difficult theory to prove rigorously. Most people do not do that until they get to graduate school, for example, in math. So it's a very specialized topic in math. At least if you graduate from our program, you will probably not hear of that again in a rigorous way. Probably never, because we don't offer that second level of advanced calculus. So what I'm going to do here, I'm going to do something, folks, like number 6. And let me actually move on to a new page and have these things on my screen. So number 6 of section 4.1, it says here, given a graph of function f of x equals 1 over 1 plus x squared. So f of x equals 1 over 1 plus x squared. Now, if you graph this particular function, you will see, and I'm not going to do decimals today because we don't really need to do decimals. We can actually do decimals, well, maybe a little later, not now. So we can do without decimals, though. So this is fairly straightforward, even without decimals. And there we go here. So if we graph this particular function, we will realize that it's going to look something like this. It's going to go through a point like this, and as x goes to infinity, you can see that the limit here is 0. So it's something like this. That's the graph of this function, this particular function. The graph itself is not so important. What's important here, folks, is that they tell us take the numbers -2 and 2 and estimate the area under the graph using 4 approximating rectangles and taking the sample points to be right endpoints and then midpoints. What does that mean? So it means that, number one, they want us to divide this interval from -2 to 2 in 4 equal parts. This is -1, this is 0, this is 1, and this is 2. All right, and this, for this, we want to build rectangles on top of this, but not just any rectangle. So we're just going to build a vertical lines. There we go, lines like that. Not just any rectangles, but rectangles that look like that, and then you use right endpoints. So what does that mean? It means that I'm looking over here and I'm looking where I hit. So the right endpoint of the segment from -2 to -1 is -1. And I'm going up here and I'm going all the way up to where I meet the graph. And then I build a rectangle with that. There we go. That's my rectangle. That's my first rectangle. You see, I'm using the right endpoint and the height right above the right endpoint. That dictates the height of my rectangle here. All right, so I'm going next, and I do the exact same thing. And because of this shape of a graph, the right endpoint would be because of the situation here, the partition, the right endpoint of -1 to 0 will be 0. I go all the way up and until I intersect the graph, and that's where I stop and I build this rectangle. Then I go next, I go one more unit over here and I build this rectangle right endpoint. As you can see, some of these rectangles end up being, having parts outside the graph and finally parts inside the graph. So these are the rectangles that we're looking at. So again, all of these rectangles, their heights are the value of the function f, which is, by the way, this one, 1 over x squared plus 1, the value of that right above the right endpoint of each of the intervals. So if the value, I can determine the height, for instance, for this one here, this one here has a height of, so I'm looking at my function y equals 1 over x squared plus 1, and I plug in -1 here, and I get 1 over 2. So the height of this is 0.5. So that point, that corner here is -1 comma 0.5. All right, that's the height, 0.5. Likewise here at 0, if I plug in 0, I get 1. So this point is 0 comma 1, this 1 point. This 1 point over here is going to be, so again, I go from here to here, from 0 to 1, above 1. I plug in 1 in the formula and I get 1 over 2 again. So this is the point 1 comma 0.5. And that's the height of the third rectangle, and the height of the last rectangle here, I'm going to use, the right point. So we use the right end points, folks. I use the right end point, 1 over 4 squared, 2 squared plus 1 is 5, 1 over 5. So this is going to be 0.2. So this point over here, let me just delete that. There we go. This point here is going to be 2 comma 0 point. So we said 1 over 5, right? So 0.2. Okay, so again, the graph that we're looking at here, this is the graph. I'm going to write the graph underneath is y equals 1 over x squared plus 1. The Riemann sum using right endpoints is, and I'm going to say here, folks, I'm going to say here is, and I'm going to add up all these things. So again, the base times height, right? So the first thing, because the base is 1, I only have to say 1 times, right? And the height for the first rectangle is 0.5 plus then 1 times the height of the next rectangle is 1 times 1 plus the next one is 1 times 0.5 plus 1 times and then we have 0.2. All right, this is the height, and that is, if you add up all of these together, this is 0.5 plus 0.5 is 1 plus 1 is 2 plus 0.2 is 2.2. Okay, my apologies, folks. All right, so this is the area that I get here with these things. Now Riemann taught us that this would be sufficient to calculate the area under the graph. This would give us a good approximation. Now, of course, you have pieces of this rectangular approximation outside and pieces inside, but the idea is that these pieces that are outside will cover the white space inside, and together they would give a good approximation here. All right, so this is the calculation with right endpoints. They also tell us to calculate this exact same sum using midpoints. All right, in this case, I am going to, again, use the exact same graph. Let me draw it again here. As to the exact same calculation, but using this time around using midpoints. So the graph is the exact same. Let me make it a little bigger like that. There we go. Exact same graph. And there's -2, and there's 2 over here. There's 1, and there's -1 and 0. And right now we want to use midpoints. What does that mean? It means that we're still going to use, the exact same, idea with rectangles, but the height of a rectangle that I want above -2, from -2 to -1 should be the value of my function f here at the midpoint. So whatever the midpoint is and whatever the value is, well, that's going to give me the desired rectangle. I do the exact same thing for the next one. So I go all the way up to here, and there we go, the midpoint. And that's this one over here. All right, I'll go all the way up to here. And let's see, what is the midpoint? Somewhere here. Yep, between 0 and 1. So that's going to give us this rectangle. And finally, over here, the midpoint would be someplace here, and that would be this one rectangle. All right, so this thing here is the area that, the Riemann sum that would approximate in the end the area under the graph. Now, what happens here, folks, is the area. So you can see that there's you can work in compensation. So this corner here would squeeze in here, and this one from here would squeeze in here, and so on. So really, it still looks like a good approximation, but the Riemann sum is now a little trickier because we have to calculate the values. Remember, our function is still that one, y equals 1 over x squared plus 1. Let me be smarter and put it here. So this is my function, and this is still the values that I'm looking for. It's just that I evaluate them at points like the midpoint between -2 and -1 is -1.5. Over here, -0.5. Over here is 0.5, and over here is 1.5. So these are the midpoints for my calculation. So the Riemann sum using midpoints is this time around -1, so it's still going to be 1. So what? So the base of these, all these four rectangles is 1. So it's 1 times, and then we have the calculation, the value of my function at -1.5 is going to be 1 over, and I'm going to write here because I'm not going to be able to do that in my head. So 1 over 1 plus -1.5 squared, right? Plus, and the next thing will be 1 plus 1 times over 1 over 1 plus -0.5 squared. Plus 1 times 1 over 1 plus 0.5 squared plus 1 times 1 over 1 plus 1.5 squared. All right, folks. So I'm going to, oops, my function disappeared. Okay, undo that. All right, so folks, I am, okay, let's say here, 2.5 squared. All right, so folks, what I do here is you can see I add up all these values and I need to do that calculation with Desmos because I can do that by hand. And I will also show you that you can do this exact same thing, the calculation of a Riemann sum in Desmos. That's not going to happen in this lecture, though, because I have some other important things to do. But let's do at least this one calculation with Desmos. Okay, Desmos. Okay, there we go, Desmos. All right, so this is the thing that's going to be there is again, so I can remember the values. So let's say f of x equals, this is easier to keep track of, 1 over 1 plus x squared. Remember, folks? There's my function graphed over there. And now with Desmos, you can actually come here and see, oh, look, there's -2, there's -1, there's 0, there's 1, there's 2. So I can simply calculate these areas, folks, by saying, you know, f of -1.5.
Are you trying to share Desmos right now? Because I personally can't see it.
I'm sorry, folks. Yep, good point. Sorry about that. Okay, 1 second. Good catch. Yeah, absolutely. All right, there we go, folks. There we go. There's Desmos. I didn't do anything intelligent here. I just typeset the value of f of x equals 1 over 1 plus x squared. Does that look good? All right.
Now.
Right. So right now I'm gonna calculate the value at -1.5, which is go down a little bit here. There we go. So which turns out to be negative that, as you can see on the graph, is 0.308, but over here is more precise. All right, plus, and then we do plus f of -0.5. That's the next midpoint. So let me represent these things. So let's represent -1.5, f of -1.5. All right, that's the point over here, this one here. So that's what's going to give the height of my rectangle. And then the next one that I want to represent is the one at -0.5. And f of -0.5. All right, that's a one over here. All right, so then we have a symmetric one on this side. So it's 0.5 and f of 0.5. All right, over here, then there's 1.5, which would be 1.5 and f of 1.5. All right, which is over here, and that's about it. So these are all the four rectangles. So their heights will be represented by the value of f at these midpoints. Again, the segments are -2 to -1, -1 to 0, 0 to 1, and 1 to 2. And we just simply add them up here on the second row. So I'm going to say plus f of 0.5 plus f of 1.5. So those are the midpoints. And it turns out that the value of a sum is 2.21538, etc. And if you compare, so just approximately 2.21, if you compare with what we got earlier by using right endpoints, you will see that you get approximately the same value, 2.2 earlier, by using right endpoints. By using, so folks, I'm hoping that you, let me just check that you all see that, because, well, all right, so yeah, you all see my my whiteboard, right? So over here, by using right endpoints, you know, with where rectangles had parts outside and parts inside, you know, you get 2.2. By using midpoints, you get 2.1. So not too far off from each other, folks. So I can say here that this sum is approximately 2.1. In fact, it's a little more than 2.1, as we saw in Desmos, 2.2, I'm sorry, 2.21. Not even 2.1, 2.21. Very close to this one here. So, okay, now what the nice thing that Riemann did, he said, folks, it doesn't really matter, as I said, it doesn't really matter which points you choose to get the heights of these rectangles. If you look at if you watch again my previous lesson, I said that basically what you want to notice, what you want to see here, you want to see that when I go over an interval of a subdivision, all that matters is that this rectangle touches the graph at some point, whether it touches right above a midpoint or above the right hand point, like we did earlier, or above the left hand point. So Riemann proved that if you make this subdivision finer and finer, so not only with 4 intervals, maybe subdivide each of these in 2 and do the exact same thing, or subdivide in 3 parts, or so on. So you can slice it finer and finer. And if you try to do the exact same trick where you build rectangles either touching somewhere the graph above each of those subdivision intervals, and you add up the areas, at the end of the day, passing to a limit, at the end of the day, you will get the correct value for the area, and it doesn't really matter which rectangles you choose in this calculation. So that's what that was Riemann's key contribution to this subject. Very important stuff, but unfortunately, again, difficult to prove with the tools that we have in hand right now. It's possible, but it will take a long time. And we're just gonna be happy to just state, well, that is the case. So let's just accept that and know how to evaluate these Riemann sums. All right, folks. So again, it's possible to do the whole thing in Desmos. So if you don't like to write these, you have to have an idea of how these Riemann sums go. Remember that not always is it true that these rectangles have a length of length of 1 here, the base. It could be 1/2, it could be 1/3, it could be something else. In fact, most of the times is numbers other than 1, but they gave us 1 here to make our calculations easy. All right, so in each case we sketched, okay, improve your estimates in part B by using 8 rectangles. So right now the next part of the question says use 8 rectangles instead of 4. And let's improve our estimate. So I'm going to do the exact same thing, but the things that we did up to this point, but instead of 4 rectangles, I'm going to use 8 rectangles, all of them between -2 and 2. I'm going to show you what that looks like, and we'll do the calculation with Desmos because it gets really messy. So, so the next deal is, so for part C, use a Riemann sum with 8. So let me write the number here. With 8 subintervals. All right, so what we use here, folks, is well, let's sketch. So we're gonna do a Riemann sum with right endpoints, and then we're gonna do a Riemann sum with left endpoints. So the first part here will be again. Let's make the curve a little bigger like that. So let's say -2 is over here and 2 will be over here. It's got to be symmetric, but I apologize, my picture is not perfect here, folks. -1 and 1, that will give us only 4 rectangles. Again, we want to focus between -2 and 2. That's only 4. So to get 8, we're going to subdivide each of these in 2 equal parts. So that's going to give us 8 rectangles. And there we are, there they are. So these are, okay, so I'm trying to get as best as I can here to drawing. And I'm going to use again right endpoints. So right endpoints means for all these intervals. By the way, this is -1.5. This is -0.5. This is 0.5 over here in the subdivision, and this is 1.5. So I'm going to use the value for this rectangle. I'm going to build it like this based on what the corner is here on the right hand point, on the right hand point of the interval. Likewise here, I'm going to go to the right. Now I'll build the rectangle this way. Over here, I'll build the rectangle this way. So there we go. And over here, I'll build a rectangle going this way. So there we go. Next thing, I'm going to build the rectangle this way again, always to the right, right? So keep to the right of it, and finally the rectangle this way, the rectangle this way, the right hand point that dictates the height of the rectangle, and finally the right hand point here dictates the height of this one rectangle here. So folks, you don't necessarily have to copy just to understand what we're talking about here. Our function is f of x equals 1 over 1 plus x squared. And what I want here, I want a sum. The Riemann sum is, I'm going to write it here, is 1/2. Because the length of this interval now, the length of the base for each of these rectangles is 1/2. So I'm going to say, instead of 1/2, I'm going to say 0.5. 0.5 times, and I'm going to take the value f of -1.5. That's the height of the first rectangle. I'm not going to worry about calculating the value because, Desmos is going to calculate that for me. Then the next thing is 0.5 times f of, what's the right hand point here at -1 plus, and then the next thing is going to be 0.5 times f of -0.5 plus, continue, plus 0.5 times f of the next right hand point is 0 here, f of 0 plus 0.5 times f of 0.5. As you can see here, the right hand point here is 0.5 plus 0.5 times f of 1. 1 is the right hand point plus 0.5 times f of 1.5. The right hand point is here plus 0.5 times f of 2. All right. So this is the entire Riemann sum that we need to use to calculate just the Riemann sum for the right hand points. And we're going to do that with Desmos. I'm not going to forget to share that with you folks. There we go. So we're not going to do this. We're not going to, well, I could represent the points. So you know what? Yeah, that's a good idea to represent all the points. We already represented the midpoints. Now we can also represent the these were midpoints earlier. Now they also are right-hand points because we have 8 intervals. So we need to represent also -1 comma f of -1. There we go. So that would be this point. We need to represent 8 points, right? Then the next one will be what's not represented, 0 comma f of 0. There we go. So 1, 2, 3, 4, 5. I got that represented. I don't have 1. So 1 comma f of 1. And then 2 comma f of 2. These were not represented, but they are now. So these are all the right-hand points of my rectangles. Now imagine that the rectangles would go from these right-hand points to the left, to the next vertical line to the left. So so they will follow like my mouse does this way, go down, and from here going down, etc. See the drawing that I made in on the whiteboard. Now the Riemann sum is 0.5 times f of, and the first endpoint, the right hand point, is negative 1.5 plus 0.5 times f of negative 1 plus 0.5 times f of negative 0.5 plus 0.5 times f of 0 plus, and this is going to be a long sum, plus the next one is 0.5 times f of 0.5 plus 0.5 times f of 1 plus 0.5 times f of 1.5, and finally plus 0.5 times f of 2. So all of these together, folks, is a big Riemann sum. Now I'm going to pull this a little. Oh, that's there we go. That's the long Riemann sum. So this whole thing is a Riemann sum. It's got 8 terms because it's 8 rectangles, as we said. And it turns out that the result is 2.207. So that's essentially apparently a better approximation. So 2.207, something like that. All right. So that's the right Riemann sum. And finally, I'm going to do the midpoint Riemann sum. For the midpoint Riemann sum, these are the right-hand points represented here. I would have to take the midpoints between these right-hand points that I represented here. So, so folks, for the I'm gonna share with you the whiteboard right now. So this is right-hand points. What we did up to this point. If you want to do midpoints, well, what you're going to have to do, you're going to have to take the exact same graph. Let's say we go this way, and I apologize, folks, and let's delete that, and let's make it a little nicer in the middle somewhere. Let's say this is a midpoint. Negative 2, 2, negative 1, 1, negative 1.5, negative 0.5, 0.5, 1.5. So now the rectangles, folks, are defined to be the midpoints over the midpoint between negative 2 and negative 1.5. And you know what that midpoint is? Is negative 1.75. So this is my rectangle. Likewise here, I'm going to take the midpoint here somewhere. There we go. There's my rectangle. All right, so that's going to be the next one. And the next one is going to be, again, midpoint here. There we go. And finally, the next one over here. There we go. And likewise, everything goes down this way. All right, then I got the midpoints, and I think the midpoint here will be the same as the one earlier, the same height. Over here, the midpoint will be someplace here. Okay, there we go. And the midpoint someplace here. Oh, well, maybe a little higher here. So sorry about that. Oops. Uh-oh. I don't want to do that. Go back. All right, so let's see. What do I need to erase? No, nothing. Somehow it kind of got erased. There we go. There's a midpoint. And finally, the last midpoint is over here at 1.75. So it's a bit tedious, folks, but this is supposed to be a similar level of approximation. So this, we saw that this is 0.20. I think it was 0.7 here. All right, so I think it was that. So now let's see if we do this one here. This is midpoints. So what we're looking at, we're looking for 0.5. All these intervals have a base of 0.5 times f of negative 1.75 plus 0.5 times f of, and the half point between negative 1.5 and negative 1 is negative 1.25 plus da da da. So we're going to add up. We're going to add up a bunch of things here, all the way to the last point here being 175. So the last point to give us a height. I'm going to calculate those directly with Desmos, folks, because the calculations are forgiving. I'm forgiving if I try, by hand. So I'm going to say 0.5, 0.5 times, and the first one is going to be negative 1.75 plus, and again 0.5 times f of negative 1.25 plus 0.5 times f of negative 0.75 plus 0.5 times f of negative 0.25 plus 0.5 times f of 0.25 plus 0.5 times f of 0.75 plus 0.5 times f of 1.25 plus, finally, plus 0.5 times f of 1.75. All right, as you can see, folks, this sum ends up being 2.217. Now, I don't know if this is the correct approximation. This is the last 3 months. I'm going to write that in Desmos there and on the whiteboard, so 2.217. 2.217. Now, by the way, this was not 0, was 2.207. So as you can see, the results oscillate between 2.207, 2.217. So it's approximately somewhere between 2.20 and 2.21, I think, the final area under the graph of this particular function. So this is the example that I wanted to do today, and this is really a long example. However, you shouldn't despair because Desmos does the job for you. So all you have to do is to understand which subdivision intervals to take and which points. So he says midpoints, take midpoints. If he says right-hand points, take right-hand points. You could also take left-hand points. In other words, you could build the rectangles based on the value on the left-hand point of your interval. So go all the way up to here by using the left-hand point as your mark, and that's going to give you the rectangle. And those rectangles are different from these here. But again, you will get a similar type of result. So that being said, so I don't want to spend more time on this because again, you could spend hours and hours doing calculations like that. I want everybody to try one of these calculations at least. And I have assigned a bunch of examples in the book, a bunch of problems. Please do those. So what I'm going to do here, I'm going to quickly start the new lesson because at least the theoretical part of the new lesson is very easy to understand. So we're going to do more next time. So 4.2, the definite integral. And Riemann said the following thing. Riemann said the following thing. If you want to calculate an area under the graph of a function, f, you would take Riemann sums. So he said, but not all the graphs, you know, not all the graphs are above the x-axis to begin with to talk about an area under the graph. So for example, there could be graphs like this. And then it has a portion above the x-axis and a portion below the x-axis. However, taking a subdivision like this, and taking the base, the length of a subdivision times, and you would take either a left-hand point or a right-hand point, so times the value of f above that point or below that point, whatever that would be, that makes perfect sense. So in other words, taking something like this, f of x star, let's call it star here, or star underneath, so you can see it's, wait a second. Oops. All right, folks, sorry about that. So f of x, let's say star over here, where x would be either an endpoint or a midpoint or any point for that matter in that interval times the length of that interval, which would be x sub I minus x sub I minus 1. Let's say that was the previous index. That makes perfect sense to take that sort of product. Now, this would represent an oriented area for the rectangle over here. If the rectangle is in the negative direction below the x-axis, would be a negative area because f will be a negative value. And if it's above the x-axis, something like this over here would have a, let's say, we have a positive value. So, so that sort of thing makes sense. It makes sense to sum that kind of thing. In other words, to put this symbol means you add up all those possible areas that we said for each index I, where I, normally people would index from 0 to, you know, to let's say 100 or 50 or something like that. So you choose a number of subdivision points, right? Because you can divide an interval in as many parts as you want. So I'm going to leave this a little loose here, the definition. So I'm just going to say the index I. You can take this kind of sum, let's say from I equals 0 to I equals n, where n is the number of intervals in the subdivision. And then you can take a limit of that as n goes to infinity. In other words, for each number n, you divide in a number of equal length interval, n equal length interval. You calculate those corresponding areas with positive and negative signs, and you can take the limit of that. And what Riemann proved, it proved that this limit actually exists. That's going to be the notion of definite integral. And would be, so if we calculate, if we do a subdivision from, let's say, from A to B, we want to calculate this limit from A to B. So we take the interval AB, and that's the one we subdivide and calculate these sums. That will be an integral from A to B of f of x dx. So he introduced this kind of notation. Now, this is very abstract. What do we do with this kind of number? So how do we calculate this kind of number? Because we said there should be an easy way to calculate this and to interpret this. Well, that's our job next time. So next time, I'm going to explain what to do with this kind of thing, how to easily interpret this kind of thing, and calculate sometimes simply by inspection an integral like that. So a formula like that. So the things are going to get easier from this point on. So up to this point, we did the heavy lifting, so to say. From this point on, you know, we're gonna see what can be done. So we're gonna find shortcuts, because without these shortcuts, again, the subject of calculus wouldn't exist and wouldn't wouldn't be as useful as it is nowadays. All right, folks. So I'm gonna stop sharing and I'm gonna stop the recording